Good afternoon, everybody. Good afternoon. My name's Tamara Davis. I am going to be your MC for the proceedings with the OzGrav launch this afternoon. So thank you all for coming. The formal proceedings will begin momentarily, but before we begin, a couple of housekeeping issues. So firstly, this is being live streamed. So hello to our guests who are watching the proceedings online. Hello also to those who have come from their industry university collaboration events today. It's great to have you here. Now, the emergency exits are at the back there and at the front. In the event of an emergency, an alarm would go off and you can proceed as quickly as you can, yet calmly, towards the exits. For emergencies of a completely different kind, toilets are located out the back near the elevators. Following the presentations today, we will have refreshments and networking at the Sky Lounge, which is just outside of this theatre. And to just also let you know, there will be photos taken at this event, and the images may be published on our website or social media pages or those of our partners. So if you don't want to be in a photo, please just let one of the staff from Swinburne know. So to start us off, I would now like to defer to Uncle Colin Hunter Jr. Uncle Colin Hunter is a proud Wurundjeri Woiwurrung elder who has worked in cultural heritage for 10 years before beginning his work in local government. He's a member of the Wurundjeri Woiwurrung Cultural Heritage Aboriginal Corporation, or WREAMS, and co-chair at Southeastern DHHS Aboriginal Working Group. Uncle, may we be welcome on this land?
Yeah, thank you. Look, I want to start by acknowledging that this afternoon or this evening, we are meeting on the lands of my ancestors, the Wurundjeri people. And I want to take this opportunity to pay my respects to my elders, both past, present and emerging, elders from all nations. But I particularly want to pay my respects to everyone tuning in today, people tuning in and people in the audience. Woman welcome. Wurundjeri Balik, Yimi Kundi Pit. The Wurundjeri people welcome everyone to land today. Wurundjeri no Gurumbo War Kundi Nagnak Lubna Pit Boli Portolia. The Wurundjeri people want to look after and protect the land as they did long before. Wurundjeri country extends from the inner city of Melbourne. It goes across the mountains of the Great Dividing Range, west to the Werribee River, south to the Mordiella Creek and east to Mount Borbor. And the Wurundjeri people are part of the Kulin Nation and of the Worong language group. Hello, my name is Colin Hunter Jr. or Willert, meaning possum. A name given to me by my grandmother as a young boy. I'm a proud and passionate 7th generation Wurundjeri man and a direct descendant of Ibogen, who is Nalangeta or head of the tribe at the time at first settlement. And it's through my grandmother, Gumbriar, meaning white dove, running tiny, or noticed she was known to a last mile, that I get Aboriginal culture and heritage in my life today, so for that I say thanks, man. My grandmother was one of the last of the Aboriginal people born in the early 1920s, up at Corrigan Mission in Healesville. I put up the Barham on the river in New South Wales. In Aboriginal culture, a great deal of respect is given to the land, the plants and animals alike. I've got a beautiful gumlos here. I'll place them out in the foyer out there. If you get an opportunity to move around this afternoon or this evening, just take an item and put it in your pocket for there in place. The significance as will keep you safe from our country and give you the access to the resources of our own country. And while you're on Wurundjeri country, most welcome to traditional lands on the waterways of the Wurundjeri people. So woman check welcome. Look, I've got to apologise because I have to go to another event in Clifton Hill, so I won't be staying. But yeah, yes, you wanted me to talk about the park over there, but there's not a lot I can say about it. So when you actually came to me when I filled out the application to go for it, gravitational waves, you know, and it just can't be the boomerang, you know. It's can't be the boomerang, you know. If you watch the first inventors, there's a lot of things in our people invented, and I think, you know, the boomerang was one of the things that helped invent the helicopter, I think. You know, so I just thought of the water and the boomerang, and it just come together. So it's not, there's a story behind it, but it's not in my head at the moment. But yeah, so I won't go and try and tell that story, but yeah. So I'm glad to see Yoshi that you get to say that every morning. So yeah, nice to have you. So thanks, Yoshi. But yeah, as I said, I've got to go. So enjoy your evening and good luck with your presentation, Matthew. Thanks very much. It's a video I can't say to listen to it, but yeah, good luck with that. Thanks for your time. I'll be back and take it early in the morning too, I think. So yeah. Oh yeah, thank you.
Thank you so much, Uncle Colin. We'll change with a little gift that we were going to. Thank you so much for coming. I am enormously excited to be here at the opening of OzGrav. It's an enormous pleasure to have the Australian Research Council Centre of Excellence for Gravitational Wave Discovery officially being launched today. It's been an exciting road for those of us who have been involved in the application and getting this going. So it's fantastic to see it coming to fruition right now. Now, when the first gravitational wave was detected less than a decade ago, it opened up a whole new window on our understanding of the universe. We could sort of, for the first time, we could now like hear the universe as well as see it. And it's a phenomenal change to be able to look out in the sky. And the only information we really had from the universe beyond our solar system was in the form of light and some charged particles, which are cosmic rays hitting our atmosphere. So to have an entire new sense, in some ways, opened up to us, and to be able to understand the universe by the ripples in space itself that come from all sorts of amazing events up in space is phenomenal. I think it's one of the most exciting fields in physics at the moment. Now, it's both an old and new field in many ways. People have been trying to discover gravitational waves for well over half a century. Many people in this room have been spending decades of their lives trying to get their first detections. But it's also in many ways a new field because the first detections of the gravitational waves have been so recent. So it's really a place that's massively ripe for discovery. And I know for me as a child, one of my first memories of getting excited about physics was when I went to a talk as a school student and someone explained time dilation and the fact that time runs differently close to a black hole compared to out somewhere in space. Blew my mind, and it's probably one of the reasons that I ended up doing physics and particularly doing astrophysics. So needless to say, I've been a cheer squad of OzGrav, the original OzGrav for the last 7 years or so, and it's really an honour and pleasure to now be joining it and be able to be Deputy Director of the Centre for this second iteration. And the group that we have gathered to be OzGrav in this second iteration, I'm really excited to be part of. So to kick off the formal proceedings here, it's a pleasure to invite Professor Pascale, Vice-Chancellor and President, Swinburne University of Technology, to give us a welcome. Thank you.
A very tough act to follow, I should say. Good afternoon, everyone, and I'm so pleased to welcome you all at Swinburne University of Technology for the launch of OzGrav 2.0, as I think it will be known. Despite the fact that Uncle Colin has left, I want to also thank him for the word of welcome, and I want to acknowledge that we're meeting today on the land of the Wurundjeri people who for thousands of years have been gazing at the skies and observing the stars, so it is very fitting that we continue in that tradition. I also want to acknowledge a special guest of today's event. We have with us Dr. Michelle Ananda-Rajah, Federal Member for Higgins, representing the Minister for Education. We have Dr. Richard Johnson, Acting CEO of the ARC. We have Professor Brian Schmidt, Nobel Prize winner for Physics and former Vice-Chancellor of the ANU. And we also have Dr. Monique Ryan, who is the local member, the Minister for the member for Beyond. And also for tonight, we have also the overlap with the kickoff of the University Industry Network, a symposium that we're organizing here at Swinburne in the next couple of days. It is quite wonderful to be here today to celebrate the next chapter of the ARC Center of Excellence for Gravitational Wave Discovery, or OzGrav as we call it. Since its launch in 2017, OzGrav has kept Australia very much at the leading edge internationally of gravitational wave research and discovery. And it has contributed to the birth, as we just heard, of an entirely new era of astrophysics. Led by our very own Professor Matthew Bales, OzGrav has already achieved many significant milestones while demonstrating its commitment to equity, to education and research. It has already made some groundbreaking discovery, including, and I kid you not, measuring the violent death spiral of two dense neutron stars via gravitational waves. The stuff of science fiction, really. But the first time a cosmic event was observed and measured in both light and gravitational waves. Another highlight for OzGrav was when scientists from the OzGrav Center made a major breakthrough in quantum physics. And again, I'm going to read the text because this is not my field. But apparently what they did was to smash the quantum noise limits by using pioneering squeezed light technology. I'm a Big Bang fan, but this kind of really tops it up. Since the center's inception, the members of the center have been honored nationally and internationally for their work. For example, 4 OzGrav members were jointly awarded the 2020 Prime Minister's Prize for Science for their critical contribution to the first direct detection of gravitational waves, which from a scientific point of view, really made a huge wave in the science world. And of course, I must mention that some of us were lucky enough to be present in Hong Kong when Professor Bales received the incredible achievement and affirmation of his work when he was awarded the 2023 Shaw Prize in Astronomy, widely known as a precursor of Nobel Prizes. Is it not, Brian? No pressure at all, Matthew, for the discovery of the fast radio burst. OzGrav has also worked on research commercialization, which is really quite important at Swinburne. We actually believe that research leads to things that are going to have an impact on society. And it has, for instance, supported spin-off company like Vice-Chancellor, which is helping shape the future of photonic sensing. With the Australian government support, through 35 million in ARC funding over the next 7 years, we know that OzGrav 2.0 will continue to make breakthrough discoveries in gravitational wave science and will deliver impactful outreach to inspire and develop the next generation of graduates. And indeed, I believe that in this presentation, Professor Bales will actually show the sort of work that he does with school children that have been working here at Swinburne. It's really important that we give the appetite, the curiosity, and the love of science to younger children, because that is where the passion for science starts. I'm really delighted that Swinburne will continue to be the home of this remarkable global collaboration. Our vision at Swinburne is to really bring people and technology together to build a better world, and we are committed to achieving our own moonshots instead of just incremental steps. We are concentrating our research efforts into a few flagship areas where we know we can actually be the world leader or work with the world leaders, and where we have the potential to become an industry partner of choice. And this is the case for space. The space industry has enormous potential. It is forecast to grow to over $1.1 trillion by 2040, with the Australian government actually aiming to triple the space industry within the next decade. We want to help develop a diverse and sustainable space industry workforce here in Australia, and through our Space Technology and Industry Institute, and because we're a dual sector university, we're working closely with industry to understand what technical and traditional skills are going to be required to build that industry of the future. By supporting the growth of space industry capabilities here in Australia and across the world, we are becoming a university that does not just look into space, but actually goes into space, from achieving our moonshots to actually going to the moon itself. Finally, I want to acknowledge how fitting it is that we are celebrating the next phase of OzGrav today, at the same time as we kick off the University Industry Innovation Network in Australia Symposium, which is underway. This week, we are very excited to put the spotlight on how to fuel innovation through the collaboration of industry and university. And the launch of OzGrav 2.0 is actually the perfect example of how it is that we can do this. OzGrav is already working with collaborators across the world, including CSIRO in Australia, but also NASA, MIT, Caltech in the US, and European partners such as European and French space agencies. And we are always ready to welcome more. Great things are achieved when universities and industry work together towards common goals. So please make sure that you chat with the staff here tonight if you're interested in partnering with OzGrav and Swinburne, as we'd love to have you come on board Spaceship Swinburne. Thank you all of you for joining us tonight. Please enjoy the rest of the afternoon, and now for Richard to share some of his view at the podium. Thank you very much.
Well, good afternoon, colleagues, and can I say what a great pleasure it is to be here in Melbourne and to be on the Swinburne campus for the very first time, and it's been fantastic to spend the afternoon here. Before I begin, may I strongly associate myself with the acknowledgement of the traditional custodians of the lands on which we're meeting today, noting that some people are beaming in, so I'm not sure where you are, but acknowledging those lands as well. And can I say on a personal note just how proud I am to be part of a nation where at the very core of both our history and our national identity sits Indigenous Australia. I think it's a magnificent thing, and I'm just so proud to be an Australian. Colleagues, over the last 10 years, Swinburne has attracted more than 170 million in government funding just from the ARC. Now, this is a tribute to the University Vice-Chancellor, and it's also so important for the community that you serve, both here locally, in Victoria, and of course for the nation. And the reason why, and I think this is put so well by Jason Owen Smith in a book that he put out fairly recently called Research Universities and Public Good, what he says is that research universities remain the most impressive machine for developing, conserving, interpreting, teaching, and using knowledge ever to be found in human history. So this is why we invest in them publicly. It's true, and it's true not in spite of, but because of our profound commitment to basic research. Basic research is just so important, and it's important for all of us, and we need to work together collectively to really tell that story. And it's something that we're committed to at the ARC. Colleagues, of course, Australia is a research nation, and it's critical that we remain a partner of choice. We've got a fantastic opportunity to build those international networks. And large research programs, as you all know, large research programs have made significance using advanced equipment and undertaking very complex experiments. They're invariably international and they're invariably multi-institutional, involving focused and collaborative partnerships with Australian and international universities, like the research centre that we're here to launch today. Look, colleagues, you are a captive audience, so can I briefly tell you about some of the things that's been going on in the ARC, because it's been a very significant period for us. And you'll be aware of the government's reforms, which culminated in the successful passage recently of an amendment bill to the agency. Key here, of course, will be the creation of an independent board for the ARC, and that board will commence in just 75 days on 1 July. Over the last couple of years, the ARC has also been strongly focused on building much better links and communicating really strongly with the sector. And we've also been taking a number of initiatives, yes, built strongly on the feedback that we've been getting, but also using our own now, so we do have some of that, to work through and really streamline and better design our programs. We're putting you, the researchers, at the forefront of the way we approach program design and delivery. Meaning we have and we will continue to strengthen our engagement and communication with you. And we've been, providing unprecedented information and feedback to researchers as we've run our schemes, and we're always looking to learn more and to hear your views. We've also been removing red tape and burden when we can. Now, it's moot whether, in terms of removing red tape, it's moot whether we can skinny down the grant application process to the satisfaction of the great German biochemist Otto Warburg, who during the Weimar period infamously applied for a research grant on a blank page with one single sentence. It said, "I require 10,000 Deutschmarks." I don't reckon we can skinny it quite down to that level, but we are working to remove red tape. And importantly, as you would all know, we're already midway through a new streamlined two-step EOI process for the Discovery Project schemes. It's our biggest scheme, and we had a huge kind of level of interest for it, with over 4,000 applications put in for the first stage. And just last week, we launched a public consultation for the joint policy review of the competitive grants program that we're doing together with the Department of Education. So it'll be another opportunity for you to have your say, and you can have your say through a public submission or by showing up at one of our face-to-face consultations until 13 May this year. Okay, thank you for indulging me on that. Colleagues, as you know well, as you really know, and many of you know this through repeat experience, ARC-funded rounds are highly competitive, and this is rightly so. We don't just fund good, and we don't even just fund very good proposals. What we fund is excellence. And that's what the public expects when it comes to wise investment of scarce resources. So, may I say to you, Professor Bales, and to your excellent team, well done and congratulations. Your proposal was assessed by leading experts, and it was one of a very small number to succeed. You've already got runs on the board, and you built another brilliant proposal, and so it's so fabulous to see you getting support from the government through the ARC. Now, gravitational wave discovery is, of course, at the frontier of science and quantum physics, a field about which Niels Bohr said, "If quantum physics doesn't profoundly shock you, you haven't really understood it." Well, if you're a house person like myself, you can learn at least to act shocked. But one of the fantastic aspects of the centre will be to use the really oddly charismatic black holes to inspire more of Australia's youth through outreach to stick with STEM. And isn't that a fantastic thing? And I can say that as a house person, so fantastic. I really look forward. I reckon that's one of the great things about the centre is that outreach and engagement. We need the next generation of researchers, don't we? So this public investment in your initiative is an opportunity to grow Australia's research capability in the deepest of deep science, but importantly, it will position Australia as a key player and contributor on the international stage. So now the ball's in your court. The ball is to continue to strive and thrive, to advance knowledge, to build partnerships, and to nurture the next generation of researchers. In concluding, may I wish you the very best for you and your team, and note that we at the ASC, of course, look forward to following your progress and success. And I'm not just talking about the mid-session report that you have to do, but I mean the success that we know that you've already been building. So now, colleagues, it's my great pleasure to introduce and welcome to the podium Dr. Michelle Ananda-Rajah, MP, who will be officially launching this great centre.
Good afternoon, everyone. Thank you, Richard, for that introduction. And I really am in the presence of greatness here. We have a Nobel laureate. We have members of this extraordinary Centre for Research Excellence. And all we need now is Netflix to complete this. If we can live stream exciting science, we're done. We've solved the game. I feel a real affinity also being here as a parliamentarian. There are 8 universities that are part of this CRC. And I have an attachment, a link to 3 of them. I did my medical undergraduate degree at Sydney Uni. I did my PhD at Uni of Melbourne, and I was a postdoc at Monash. So there you go. So I will accept Professor Schmidt's accolade when he said that I'm well suited to give this speech. I'm not Jason Clare, but I'll take it. It's a pleasure to be here with you all today to officially launch the ARC Centre for Excellence for Gravitational Wave Discovery, otherwise known as the OzGrav Centre. And I just want to note that it's a real mark of great scientists that they can distill super complex concepts and ideas down to to simple messages that we can understand. And when Tamara stood up here and said the universe is speaking to us, then it made me think, well, humanity is listening thanks to OzGrav. So that's pretty amazing. I too would like to acknowledge the traditional owners of the land in which we meet and pay my respects to their elders, past, present, and emerging. And of course, our First Nations people were the original scientists, and there's no doubt that they gazed at the stars and it helped them in many ways, likely navigation, but also just inspiring, made them think like us, pique their curiosity. There's no question that happened. I would also like to acknowledge the distinguished guests here today, including Dr. Richard Johnson, Professor Pascale, Professor Matthew Bales, Professor Tamara Davis, and of course Uncle Colin for his lovely welcome to country, a uniquely Australian custom and one that is noticed by our international allies and partners. The Australian government, through the ARC, funds research excellence. The recent passage of legislation, the Australian ARC Amendment Bill 2023, highlights the government's commitment to and acknowledgement of the ARC's critical role in actively shaping and impacting Australia's research landscape. It positioned the ARC as a leader in administering funding for excellent, pure basic, strategic basic, and applied research in all disciplines except health and medical research, under the auspices of the National Competitive Grants Program, the NCGP. The Australian government, through the NCGP, will invest approximately $895 million in 2023-24 to support our best and brightest researchers to explore, discover, and deliver outcomes that benefit the nation. ARC funding rounds are internationally recognised as being highly competitive and enabling world-leading research excellence. As a medical doctor, I know firsthand how important research and innovation are to addressing some of Australia's toughest challenges. I know how hard it is to get grants. So well done. I understand some of the barriers innovators and researchers face, particularly early career researchers. I was that person once upon a time. We really do need to make it easier for you to clear the pathway. Being awarded funding through the ARC's highly competitive grant process is therefore something to be extremely proud of. This support will enable world-leading research excellence. Congratulations to Swinburne in particular. As one of Australia's leading universities, Swinburne has been awarded more than $100 million in ARC funding over the last 5 years, with more than $46 million awarded in 2023 and $7.38 million in 2024 to date. Swinburne's contribution to research continues to increase both nationally and internationally as it delivers research that translates new discoveries into social, economic, and environmental outcomes. And your research here at OzGrav will be no exception to that. The OzGrav Centre is one of 11 centres of excellence funded in 2023 as part of a $385 million government investment in the ARC. The OzGrav Centre was awarded $35 million over 7 years. It is centres like this that will provide innovative benefits and strengthen Australia's international standing in research. The OzGrav Centre aims to use gravitational waves to investigate the fundamental nature of gravity, ultra-dense matter, and cosmology. Did I say that right? I'm much better at medical speak. The research conducted will generate significant discoveries that position Australia as a leader in developing gravitational wave megascience instruments of the 2030s and 2040s. Through impactful outcomes, the OzGrav Centre will inspire the next generation of Australian scientists and engineers whose talent underpins the nation's defence and space industries, but so much more. I mean, the spillover effects are massive when it comes to basic science, applied science. We're talking about industries And it dovetails nicely with the Prime Minister's announcement for a future made in Australia. We want to bring manufacturing back. We want to revitalise our industrial base in this country. We are at the moment at the bottom of the OECD when it comes to sovereign manufacturing capability, and the research and the innovations that are derived from centres like this will be absolutely pivotal to our nation, the next chapter of our nation's prosperity. The investment is also generating strong national and international collaboration with universities and industry partners, contributing a further 9.7 million in cash and 226 million in kind contributions. That is the multiplier effect of basic science. This significant collaboration will allow connection and research with leading experts, researchers and institutions, and share their groundbreaking findings with a national and global audience. The OzGrav Centre's research will be integral to scientific exploration, pushing the boundaries of our knowledge and contributing to key research priorities to address the most important challenges facing Australia today. Congratulations again to Swinburne and Professor Bales and his team. It is my great pleasure to officially launch the ARC Centre for Excellence for Gravitational Wave Discovery.
So now to do the official proceedings of the launch, I invite you to officially open the centre by drawing the curtain and revealing the plaque.
Big reveal.
Can I also invite the other speakers up to and have a couple of photos for this moment? And Karen as well.
For the photos.
It's incredible.
I like it so much. It's sensitive. Yay. Thank you so much for all the amazing words that have been said so far. Without further ado, I would actually like to invite Professor Matthew Bales to the stage to tell us a bit more about the details of OzGrav. Take it away.
With my microphone. I like to roam around, but I actually like neutron stars and pulsars and black holes much more. And I think one of the reasons I'm here is just that I've loved understanding how the universe works and the laws behind it since I was a little child. When I was about 6 years old, mankind landed on the moon, and it really captivated the nation with a tremendous feeling of excitement. And I remember we actually had a special holiday in South Australia, and we got to go home, and my mother dragged me out and sat me in front of the TV, which was a big black and white thing with a 26-inch screen, and you had to sort of hold the aerial to get not fuzzy. And I remember seeing Neil Armstrong landing on the moon, and it was a truly inspirational moment, and I'm sure that propelled me into science, and it's probably why I'm here today. I think scientists have a role in what I call the post-truth society, to actually use evidence to make decisions and be an exemplar to the rest of society about how you should judge evidence and make decisions. And I think our research is so fundamentally linked with evidence, statistics, and basic science that we wouldn't get anywhere if it wasn't. And so I feel scientists have an obligation to show that there can be laws that govern the universe, and we can test them, and we can keep testing them until they break, and then we need new laws. In the same way that Newton's laws couldn't explain black holes and neutron stars, we needed general relativity. So today I'm going to give you a little virtual tour of the universe and explain what OzGrav will get up to over the next 7 years. I'd like to thank the member for Higgins, if I can use that word, and for the check, and I really do love the ARC. It's been incredibly kind to me. And they even sent me a lorry pin when I lost it and announced that on Twitter. Okay, so I'm Matthew Bales. I've been at Swinburne since 1998. I've been in love with astrophysics since the moon landing, and especially Carl Sagan's magnificent ability to convey a sense of excitement about the universe and this wonderful universe in which we live, that we can take nature's laws and explain the phenomena we see. We've got a beautiful artist, Carl, who's around here somewhere, down there, who's made this beautiful rendition of two neutron stars orbiting each other and sending out a spiral of gravitational waves throughout the universe. And that's partly why we're here. We try and detect these things. I'd just like to start by adding my own respectful acknowledgement of the Wurundjeri people of the Kulin Nation by the traditional owners of the land on which Swinburne's Australian campuses are located. And as a little boy, my first science project was actually about the platypus. And my parents drove me from Adelaide to Healesville, and they had one of the few platypuses in captivity. And I remember just having my nose pressed against the aquarium and seeing it swim around. And that really ignited my first research project. And I learned all about the platypuses. So I always get a special fuzzy feeling when I take international visitors out to Healesville. And it's quite sad when you read the history of the Aboriginal people that were interned up there and then kicked off their land basically for the second time. And so I'm sorry Uncle Colin can't be here. I myself have Indigenous second cousins, and it's not a great surprise that I'm the one who has the PhD in astrophysics and is able to open this centre, because my second cousin Len Bales was actually taken from his mother when he was 4 years old. And I get quite emotional feeling when I discuss that, because the opportunities I've had really can't be compared to that. So optical astronomy first used telescopes to look at the sky over 400 years ago, when Galileo took his telescope and pointed at one of the planets. The planets were the wandering stars in the night sky, and he was shocked to see, and this is his original handwriting, which I can't really make out, but these are images of Jupiter and where the 4 Jupiter moons were. And even with this reasonably crappy telescope back in the 1600s, he could make out the moons. And if you ever get the opportunity to get one of the telescopes and point at Jupiter, it still has a sense of wonder, even better than Saturn's rings in my view. And he showed that every night the planets were moving around. These days we can send space probes to Jupiter, and we can also illustrate how the 4 moons circle Jupiter, which is in shadow here because unfortunately it's on the other side of the sun. But Io actually goes around Jupiter twice for every once that Europa does, and it goes around twice for every orbit of Ganymede. And we can now understand that in terms of resonant orbits. But we can send satellites and bring back remarkable pictures of what these moons look like. So optical astronomy has had continued investment for over 400 years. And we now are building remarkable facilities like the James Webb Space Telescope. And I was very impressed by Karen's little brooch there, which is in the shape of the mirror. Well done, Karen. And this telescope literally has 1 million times the sensitivity when looking at the distant universe than any predecessor. And there's lots of my colleagues here at Swinburne that are witnessing the birth of galaxies for the first time. Radio astronomy is another discipline, again in the electromagnetic spectrum. And I've spent about two years of my life at this place. This is the Parkes Radio Telescope. Little did I realise that it had been involved in a pivotal discovery on my birthday back in 1963 when a paper came out announcing the discovery of the quasars. Quasars are now widely believed to be a supermassive black hole, creating a disk of material and squirting these jets of material out, which have an extension over 1 million light years. And this is a true image from a radio telescope showing these jets, and this is our sort of artist's impression. Australia's been investing in radio astronomy since the 1940s through the CSIRO, And in the 2020s, we won the right to host the Square Kilometre Array, which both the preceding Liberal government and the Labor government have given bipartisan support to. This is going to be a $500 million instrument built in the Western Australian desert. And the technology for Australian or under Australian development in the form of the phased array feeds led to the creation of the Quasar-Sat spin-off company, and one of the OzGrav Mark I spin-off companies, Space, has been developing the receivers for Quasar-Sat. So it actually took me a long time to realize that if you used a satellite dish to look at a pulsar, you could also use a satellite dish to look at a satellite. But there you have it. And of course, this investment in this technology that pushes the boundaries of science leads to industrial innovation. And the most widely quoted example of that is, of course, Wi-Fi. And when I joined CSIRO back in the 1990s, I asked the person opposite me, "What are you working on?" And he said, "I'm trying to get Ethernet on something the size of a credit card so that you can carry around your laptop and be on the internet." And I thought, well, that would never work. And most of those guys are now multi-millionaires. Still, Einstein was a great thinker, and whilst a patent clerk, he used to think about how the universe worked. And indeed, to him, I think it was very logical how it must work. And he developed the theory of special relativity back in the early 1900s, and about 10 years later, he generalized that to, in his general theory of relativity, to incorporate gravity into relativity. And he used to conduct these wonderful thought experiments, and one of them was, if you were in an elevator on the Earth, you would feel a gravitational force. Would you be able to tell the difference if you were in a closed soundproof elevator between that and being accelerated in the voids of space, millions of miles from any mass, and accelerating at 9.8 meters per second squared? And to his mind, you wouldn't be able to do any experiment that could tell whether or not you were on the Earth or whether you were accelerating. He thought about it a bit more and thought, well, what about if that elevator was free falling under gravity, or whether it was just sitting still in outer space? If you were doing an experiment here, like firing a laser beam off a mirror or between two mirrors, would you be able to tell whether you were free falling or not accelerating at all? And again, his conclusion was that maybe you can't. And so maybe we need laws of physics that will operate the same in a free falling elevator or being in the middle of the voids of space. And so he developed his strong equivalence principle. And some of the consequences of that is that light should bend around bodies, that clocks, and Tamara like this one, should tick more slowly near a gravitational field than far from it. And indeed, they should stand still if you could get near the edge of a black hole. And that space is compressed. If you grab a meter ruler and you take it into outer space, it should actually stretch. And if you come right next to a black hole, it should be squashed infinitely small. So he realized that if you could actually compress something sufficiently according to this equation, and this is one of the few ones I have in my book, just 2gm(c²), put this into context, if you could take the Earth and squeeze it down to something with a radius of 1 centimeter, you could turn it into a black hole. That's not very easy. In fact, Einstein wondered whether black holes would exist at all. Then you would get something that was so dense that not even light could escape it. He also realized that if there was any equivalence between electromagnetism and gravity, in electromagnetism, we knew that if an electron goes past a proton, it gives off a photon, this light. Maybe if two massive bodies went past each other, they would give off a gravitational wave. And because they have the same effective charge, or a positive mass, this gravitational wave would be quadrupolar. And if I'm a gravitational wave, I'd be stretching and squeezing in this direction and simultaneously, in the opposite sense, distorting a circle into an ellipse in an opposite way. You can compute how large this signal would be for something like the Earth and Moon. And I had a work experience student do this the other day, and little h would only be about 1 part in 10 to the 24. So if you could build a gravitational wave detector much bigger than what would it be? It would be the orbital period of the Earth times the speed of light. You'd have to be able to measure a change in the distance of 1 part in 10 to the 24 to be able to detect this. So Einstein himself thought this is ridiculous, this will never occur. Gravitational waves are a fanciful notion. He even tried to retract his paper, but luckily the referee said to Einstein, no, actually gravitational waves do exist, you just don't understand their own theory. And Einstein was so annoyed, he never submitted another paper to that journal ever again. But luckily he was wrong. And to me, I got so excited about this field during my honours work at the University of Adelaide when I was introduced to this object. This is something called the binary pulsar. It's 2 neutron stars. One rotates every 59 milliseconds, and it goes around a companion star every 7 3/4 hours. And so a year in this system is just 7 3/4 hours, and the relative speed at the closest point is almost 1,000 kilometers per second. The orbit of Mercury is also elliptical, and it precesses by 43 arcseconds a century. That's much less than a 60th of a degree per 100 years. In this system, the orbit precesses by 4 degrees every year. And so this is the most relativistic laboratory, or was the most relativistic laboratory ever discovered back in the 1970s by my friend Joe Taylor. And people soon realized that these systems are so close, they should be emitting copious amounts of gravitational waves. And even though the distance between the neutron stars was over 1 million kilometers, it should shrink by 3 millimeters in orbit. That's about this much. Now, if you're only shrinking by 3 millimeters in orbit, that's about a centimeter a day. It takes 300 million years for this system to coalesce. But when it does coalesce, it gives off an amazing burst of gravitational waves that would propagate throughout the universe. And if you took a boomerang-shaped detector and you fired a powerful James Bond-style laser into it and sent it down vacuum tubes 4 kilometers long, when the light came back together, if one of these things had coalesced somewhere in the universe, it should move your mirrors by about 1/10,000th of the width of a proton. And for my friends at ANU, that's easy to measure. And so partly due to the magnificent quantum squeezing that they've introduced to detectors, but also many of my other colleagues working on the detectors, gravitational waves were discovered back in 2015, about a month before the assessment panel for our first Centre of Excellence. It was excellent timing. So Joe Taylor dedicated his life to measuring the decay of this orbit. So if you shrink by 3 millimeters in orbit, after 2 orbits, we shrunk 6 millimeters, then 9, then 12. And the time it takes you to get back to the point of closest approach grows quadratically, sort of y equals x squared. And this was the Einsteinian prediction, was this parabolic line here. And these were Joe's experimental data, along with my good friend Joel Weisberg. And about 1993, they were awarded the Nobel Prize for proving that gravitational waves existed. And indeed, this system was the impetus to build the Advanced LIGO detector. And it might be hard to believe that one object could trigger billions of investment, but it did. And then they stopped observing for some reason after the Nobel Prize, and then started again later. So a Nobel Prize is not always good for
Terrible for productivity.
So just prior to the merger, the 2 neutron stars, even though they're 20 kilometers across, if you take a teaspoon of a neutron star, it would weigh more than all of humanity, even with the obesity crisis. And these 2 stars actually travel around each other 1,000 times a second. So the orbital period is 1 millisecond. It's not long before they rip each other apart. You get a new star appearing in the sky. And indeed, OzGrav was fortunate enough to be able to witness the first of these neutron star mergers. But the first gravitational wave was something completely unheralded, and that was 2 30 solar mass black holes. So here we've got the blue and the orange signals, or what the 2 different detectors in America detected, a bunch of noise, and then a little what we call chirp. This chirp looks remarkably like the OzGrav logo. and those two signals were matched, and I think it was 7 milliseconds between them. And this was the discovery of the first gravitational waves directly, not just being inferred. 2 years later, we had the first neutron stars merge, and a new star appeared in the sky for about a week, and that was observed by OzGrav scientists using the ANU's telescope. And then later that year, the Nobel Prize in Physics was awarded to the three major players in the development of the Advanced LIGO detector. And I think many of the people in this audience got a 1/1000th share of the various other prizes, like the Breakthrough Prize and so on, that were awarded. We were fortunate enough to be awarded the Prime Minister's Prize for my more senior colleagues who had been working on this stuff for 20+ years. There's now over 100 gravitational waves that have been detected with the LIGO detectors, and these are the projections of how this field is going to continue to evolve if we keep investing in it. And our message to the ARC's expert panel was you don't want to start working on this new area of research, a new window on the universe, work on it for 7 years and then stop. So the advice was from the ARC, never submit a rebid. We thought this is so important, we have to. And I can't tell lies, so it was a rebid. So thank you, Richard, for making an exception that proves the rule. So we've detected some remarkable mergers. This one I'm particularly fond of. It was a 100 solar mass black hole with a 77 solar mass black hole, producing a new black hole. The mass deficit here is the amount of energy that comes off in gravitational waves, which means we can detect the source. And Carl did this beautiful graphics. We're hoping that our current observing run, affectionately known as O4, is going to produce over 200 detections, and that by increasing laser power and clever technology, we'll keep this field going until we're detecting 1 million sources a year. So why OzGrav and why now? Well, our mission is to use gravitational waves, not just as something we detect, but to use them as a tool to explore the fundamental nature of space-time and gravity, ultra-dense matter, and ultimately cosmology. And in the Australian Decadal Plan, there are words that suggest that we should be funding the design and development of the technology necessary to build an Australian gravitational wave pathfinder and hopefully a future Southern Hemisphere detector. There's currently 5 operational gravitational wave detectors in the world. They're all in the Northern Hemisphere. It would make a lot of sense from a triangulation point of view to have one in Australia. A very geographically stable continent with a stable government. That funds pure research. So this is an idea of this is what I call the discovery wheel. If you squint, this looks a bit like an O and this looks like a Z. So we had the original OzGrav up until 2023. We've got the new one in 2030, and we've got the mega science detectors that this will lead to in the future, the Square Kilometre Array LISA, a space-based gravitational wave detector, and the 3G detectors. You can really start anywhere of these interlocking circles. I like to start in physics. Einstein had his theories of gravity. We wanted to explore whether that was right, so we built the instruments necessary to detect the gravitational waves. We made the discoveries. That opens a new series of physics questions, which involve a renewed investment in instrumentation, and hopefully we'll go around this wheel for many decades to come. I've been joined by Tam, which is an amazing individual. When she's not winning prizes and representing Australia and so on, she does science. David McClelland leads our instrumentation team, and we've got many new scientists joining the OzGrav story, particularly with the acquisition of the University of Sydney and University of Queensland. We've more than doubled the number of female scientists working in this very technical and physics-rich area, and we hope to keep pushing ahead in that regard. Our core research capabilities really depend on both electromagnetic, gravitational wave, and space-based detectors. You'll be happy to hear, Pascale. And we have the OzStar supercomputer Ngaro Tinderbeek, which the Victorian state government invested in only last year. Our main collaborators are in Europe and the US, and these are the world leaders in gravitational waves. So we have 6 key projects. All of them span our different universities. I was talking to Brian before about how the centers of excellence are the best thing the ARC does. It really does get you collaborating. And this is my 3rd center that I've been involved with. And I think it really has led to a cohesion of the astronomers across Australia, and long may it continue. So we want to have an agile and dynamic workforce that can work on different projects and really bring critical mass to significant projects of international scale. So the first thing we're trying to do is actually make the detector work better. These are sensitivity curves, and as you go down, you can see further out into the universe. One of the great things about gravitational waves, if you get a factor of 2 increase in sensitivity, you get a factor of 8 in volume and an exponential growth in science. This work's mainly being done at Adelaide, UWA, and ANU. Once we've optimized the detector, we'll be detecting many more things, and Tara Murphy up at Sydney and Eric Thrain at Monash are leading the detections key project. This is really of crunching the numbers on our supercomputers and detecting as many sources as we can. We're going to be using observatories on the Earth to observe a network, a galactic scale gravitational wave detector using pulsars. And Ryan Shannon is leading this work out of Swinburne. We're going to be working on what is the nature of black holes. Do they spin? What is the fundamental nature of space-time that this new window of the universe opens? And we'll be using the square kilometre array to monitor neutron star transmissions to map the precisions of orbits to sub-millimetre accuracy. It's a great mystery as to what is the state of nuclear matter. How big is a neutron star? This is a very difficult question to answer, and we're going to be using our telescopes and the gravitational wave detectors to watch while neutron stars rip each other apart and to see how signals propagate throughout or past massive bodies. And this is data from one of our radio telescopes showing the curvature of space-time as you go past a super dense star known as a white dwarf. And then finally, cosmology, the final frontier, if you like. Brian won his Nobel Prize for measuring the fact that the universe was accelerating. Unfortunately, if you take the much more simple physics behind the Planck Observatory, you get a different answer these days. So this has brought Brian out of retirement from being a Vice-Chancellor, and we're hoping to use neutron star signals to break this tension. Well, who's right? Is it Planck? Is it the supernova distance ladder? And so we can use the amplitude of the gravitational waves to work out exactly how far away a neutron star merger takes place. If we can pinpoint the galaxy, we'll get the redshift. And so we are hoping to make great contributions in this area. We've also been pioneers in fast radio burst detection, and this gives an alternative way of measuring how many electrons there are in the universe, and thus how many baryonic particles. And you can also use that to get an alternative handle on the mass density and also the scale of the universe. The universe is actually full of these voids. If you start with a uniform sequence of particles and let gravity do its trick, it doesn't take much asymmetry in the original distribution to lead to these beautiful structures. And we're going to be peering through these galactic voids, both at fast radio bursts and coalescing neutron stars and black holes, to understand the nature of the universe, its age and chemical composition. And then finally, we need a future. We can't stop at 2 centers of excellence, Richard. We've got a future technology project, and this is about squeezing the most out of our laser beams, increasing the masses of the mirrors. There's something like over 1 megawatt of power inside a gravitational wave detector. It's very easy to melt your mirrors, and our friends at the University of Adelaide are good at trying to keep them clean and thus cool. And so we'd ultimately like to be contributing to the technology that's going to drive this area forward in the future. and be able to possibly build our own gravitational wave detector that uses that technology in the future. These new observatories are remarkable. The Europeans are getting behind something called the Einstein telescope. It's going to be an underground triangle of 3 10-kilometer long vacuum tubes underneath the Earth, if they can agree amongst themselves which country should host it. The Americans are hoping to build a 40-kilometer vacuum tube in a boomerang shape, I'm going to call it, to measure even further. And we should be able to see every black hole merger in the entire universe, as well as detect thousands of neutron star mergers. This is our vision for what an Australian detector might look like. There's some biases as to where it should go. We need a very stable place far from a city. And the idea is that we would be exploiting high power techniques to study the nature of neutron star matter. People development is absolutely essential to any successful centre of excellence. We've been encouraging an entrepreneurial culture at OzGrav for many years, and these two gentlemen, James and Lyle, were a postdoc and a student at ANU. They realised the same technology that could lead to the astounding precision that you can undertake in measurements using laser beams could be applied not just in gravitational wave detectors, but in everyday life. They formed their own company, thanks to a $20,000 grant from the OzGrav executive, and they sold it for many tens of millions of dollars to advanced navigation. And this is a really great Australian success story, but also a success for the ARC and ANU and everybody in the OzGrav team. So we'll be encouraging this type of culture in the next centre as well. Career development is not just about forming companies, but also creating the next Matthew Baleses and Brian Schmitz. So we're going to be training over 150 postdocs and PhD students. We have tremendous employment rates for all of our graduates, mainly in our science, but also in data science, space, defence and mining and advanced manufacturing. We've seen the benefits of equity, diversity and inclusion. We have our own EDI committee that I lead as director to reinforce the importance of this in the centre. Karen's been good enough to give us an Indigenous and a pro-diversity fellowship, and we'll be looking at who's going to take this field forward in 7 years' time. Outreach is something that comes naturally to astronomers. People want to know about space. Tam here is appearing on the ABC Catalyst show, and that's how big the Earth would be if it was a black hole. We're blessed with a lot of great communicators. People like David Blair dedicated his life to preaching the gospel about Einstein and his laws. A lot of our students really enjoy going out to schools. And I'm just going to give you a flavour for some of what we might do. How am I doing for time, Michelle? Oh, awesome. So we've developed a tool called OzGrav's Virtual Universe, and it enables you to fly around the universe and get kids excited about space. It runs on any laptop, but you can easily morph between planets. This is Olympus Mons on Mars. This is Jupiter up close. This is Saturn, and the curriculum tends to stop at Neptune these days. So we have to be very sneaky about how we talk about black holes and neutron stars. And so we've actually developed an activity where students can explore the motion of the Earth around the sun by looking at pulsar signals. And pulsars are these remarkable naturally occurring clocks in the universe. You can work out when each pulse hits the Earth to a millionth per second. So that's a microsecond. And so what we do is we teach the kids about whether the Earth is going around the sun or the sun is going around the Earth. And then we provide them with data from the pulsars, and they can map the position of the Earth in absolute space and find out whether the Earth is just sitting still or whether it's actually going around something. And so this is something I've been getting work experience students to actually develop a lesson, because I think it's much more powerful if you can go to a school with kids that have actually helped develop the material. It makes it much easier for students to think, maybe I could be like them. So we've got some role models here in the audience who are working with me every week. And we've taken some data just last week. This is very hot off the press. I had a bunch of students plot the position of the Earth. Our observations weren't very often at first, so it was a bit chunky. But then you get these beautiful sine curves, and this is showing the delay from a signal from a neutron star when it hits the Earth. And if you plot a pulsar in 90 degrees apart, its delay, you can actually get a nice double sinusoid. And you can use that to map the Earth's absolute position in space, and they can see the beautiful elliptical path of the Earth around the Sun. I first trialed this in South Africa, and if you think our schools have some funding issues, you should visit this school. It was quite interesting. The projector didn't work, so I had to suddenly improvise. But these kids really loved the lesson, and they were calculating the velocity of the Earth and its motion. It was interesting, the questions I got from them. Normally it's about black holes and neutron stars. They just wanted to know what I learned. Because even though this was quite a rich school in South Africa by black standards, their sole purpose was to get a job and earn a living. These are some of the students we've had as part of the Astral program here at Swinburne. They came in for 3 weeks and we did a real research project where they were trying to detect gravitational waves from supermassive black holes with myself and Dr. Flynn. Because I fell in love with this system of the two neutron stars merging back in 1984, when I was an honours student, I realised that we actually had some data lying around from something called the double pulsar. These are two neutron stars that actually go around each other 10 times a day. And so I went to Hong Kong and gave a lesson there over 2 hours. And this is Esther, who was one of the students at the Australian Hong Kong school. And she and her class measured when the two neutron stars in that system actually came back to the closest point, and we plotted it. And then we plotted the Einsteinian prediction. And they could tell that this system actually shrinks by 2 millimeters per orbit. And that was a really nice way to close out, for me, what would be a 40-year journey since first learning about this system and being able to get school kids to see the effect of gravitational wave emission on a real neutron star binary system. So just to finish up, this is one of our plans for Swinburne. We want to build something called the Digital Experience Room. I like to call it OzGrav's virtual universe. The idea is we're going to get a bunch of LED walls and be able to power them with a computer. We've got some of the software engineers here that are working on this project, and we want to have children come in and learn about space in an immersive environment. We booked some time out at Dream Screen in northern Melbourne, and we went and looked at what it looked like, and this is me standing under Mars. So I think this is going to be a great way to get kids in and teach them about space. And this technology will be available to all our partner universities across Australia if they have these LED walls. So what will our legacy be? Well, hopefully we'll be making landmark discoveries in fundamental physics. We'll develop a high-tech workforce for industry. I'd like to think there's going to be some instrumental leaders coming out of the centre, training the next generation of Australian scientists, having a very engaged pro-STEM community that learns that you can make predictions about the universe and the Earth based on physical principles like climate change, and they should pay attention, and hopefully we'll provide a foundation for an Australian Gravitational Wave Observatory. So I wanted to thank Uncle Colin, the senior members of the executive group here have supported me in one guise or another since 1998. The ARC CEO, Michelle Ananda-Rajah, for Higgins and the $35 million check. My deputy directors, my fellow chief investigators, we really put together an amazingly strong team for this bid, and even though it was 857 pages long, I thought it was flawless. And all of the staff and students of OzGrav, and thank you for your attention.
Thank you, Matthew, and congratulations for bringing this all together. Now, we are moments away from drinks, so I won't keep you much longer. But to conclude, just wanted to thank the government and the ARC for supporting the Centre of Excellence program in general and for trusting us with the responsibility of discovering new things about the universe. I genuinely believe this kind of thing enhances Australian society, not only through inspiring the next generation, but also through directly training people and developing technology and computational expertise at the highest level in our workforce, which then passes through in the industry in Australia as well. This kind of support is what allows Australia to achieve world-leading research and enhances our international reputation. Every single one of the OzGrav members, of which there are going to be hundreds over the 7-year course of the centre, is going to become an amazing ambassador for Australian technology overseas. Now, having been part of the centre before, I know just how rewarding it is to be part of one of these groups, and a lot of that is just to be part of the amazing community that is brought together by the centre programs. So I was just going to say, of the OzGrav members, OzGrav 1 and 2 in the room, can you just give us a wave? I believe we've got stars on, so if you're not an OzGrav member and you'd like to hear more about black holes and stuff, come and have a chat in the reception that immediately follows this. I'm super excited to be working on these amazing projects for the next 7 years with everybody. So let's go celebrate.